Well, I think I will get going. Let me start by saying good afternoon to everybody and thank you for attending my talk. My name is Jerry Thomas. I'm from Milwaukee School of Engineering. I've been an adjunct professor there for about 15 years and currently teaching online like everybody is. So this online experience is getting, wouldn't say old hat, but it's certainly becoming familiar. So what I'm going to do is, let me start what I'm going to talk to you today about is based on work that I've been doing for a number of years. It's based on an observation that the game theory of von Neumann and Morgenstern is equivalent to a field theory of games. And based upon looking at game theory as a field theory, I've been looking at the geometry that results from that theory and the equations that result from that theory. And those equations provide a way of describing the time sequence by which individuals or groups of individuals make decisions and how those decisions might change over time. And that process of making decisions and the changes that are made in those decisions looks very much like a theory of fluids, and the behavior in fluids looks very much like the fluids that you would get in the Navier-Stokes equation. I won't kill you with the math, but if I actually were to write it down in geometric notation, I would have an Einstein-type theory, but not in 3+1 dimensions, but in general in n+1 dimensions. And I would have equations that would tell me the rate at which things flow. This would be the rate of change v, which would be a flow. It would depend upon some stresses in red, and the equations would have some geometric constructs. Covariant derivatives might have Coriolis forces, for example. And specifically in game theory, the Coriolis forces are very, very important because those directly relate to the game matrix from von Neumann's theory. So in trying to understand those solutions for game theory, there were a number of challenges. And the first non-trivial challenge is that the equations that result are nonlinear partial differential equations. So originally I wanted to use NDSolve for those equations. That was very tough, but with since release 12, I guess, we can solve PDEs that are nonlinear, and that makes my life a lot easier. I can apply it directly. The next challenge is that even for very simple processes, two people playing a game, each with two strategies, and we look at steady state, so we can take time out as remove time as a variable. The partial differential equations are in 5 dimensions. An even simpler game, you might think, which is tic-tac-toe, has 13 dimensions. Another problem or challenge with the game field theory of games is the compression terms. The fluid is not, the fluid may be compressible, okay? So the compression terms are not 0. And you might think this would be hard to do such things as compute streamlines. There are a couple of solutions to that one. Of course, one is simply you assume the compression terms are 0 and go ahead and compute the streamlines. Another challenge, of course, is assuming that we were very strong and we can get exact solutions to our partial differential equations in any number of dimensions we like, there's a challenge of visualizing what those solutions mean. So the way we've attacked it so far is to look at streamlines, ignore the compression terms, and look at streamlines either in 1 dimension and also generalize the idea of streamlines to 2-dimensional streamlines. This gives us a little bit more insight into the geometry. What we'll do today is in looking at the solutions that I've done so far, my concerns are particularly with the compression terms and not getting accurate results and not understanding whether those, to what extent those compression terms that have been ignored change the qualitative nature of the solutions. So a way to study that is to go back to a problem that we can compute directly, exactly, which is a three-dimensional problem. And so what I'm going to do today is talk to you about a three-dimensional Navier-Stokes problem, slightly changed to make sure that it has some aspects of the game theory solution I'm interested in, but otherwise is a perfectly legitimate Navier-Stokes problem. So here's what it would look like. So the equations would look like, on the left, these are the flow equations that you would normally have. A flow vector times a gradient in x direction and y direction, z direction, and it would depend upon it would be equal to the gradient of pressure, possibly the gradient of a gravitational field, and a convection term that would be related to the Coriolis force. All of these are certainly possible things to have in our three-dimensional space. One of the modifications from game theory that I want to impose is allow a different coefficient for, say, two of the directions, say x and y, which I will call player one, and in the z direction, which I'll call player two. Whether they have any real meaning in physical fluid, I'm not sure, but the purpose of this study is more mathematical than to try to create a physical fluid with these attributes. I need to make some assumptions about the values of the payoff, which I just take nominally. The values, I'll add some gravitational field, I'll add some stress, phi 1, and provide a boundary condition, okay? Now the key for the boundary condition will be, in general, I could pick the flows along the boundary. These are Dirichlet conditions, and I could pick these flows to be zero, or to mimic some of the things that we might see in a field theory of games. I've assumed that the flow, say in the x and y direction, are as stated, something along the x direction, something along the z direction. The gradient for player one, i.e. the gradient along x plus the gradient along y, is a certain value. Along z is negative of that value. So I'm going to assume on the boundary that the normal compression term is zero. I could have taken all of these terms to be zero, for example, and get, of course, slightly different solutions, but some of the qualitative features that we're going to talk about don't appear to be dependent upon these things. I should say, if I were to take all of the terms to be zero, as an example, all the flows along the boundary to be zero, all of the stresses in the gravitational fields to be zero, my flows in the end should be zero, which they are. If I start adding back some stresses, they essentially pull stuff off the boundary even if the flows were zero. So I generate compression inside the boundary. So that's one of the things we hope to see in looking at the solutions. So we're going to use these boundary conditions and the modified Stokes equations that I showed you above, and we're going to solve things with NDSolve. I'm really very happy now that NDSolve is truly simple. All I have to do is say NDSolve and all those complicated equations go away. I've not tried it in n dimensions with a full n-dimensional solution, but I have tried it with n-dimensional problem solutions for the game theory for streamlines, one-dimensional and two-dimensional streamlines. And even though the number of variables is very, very large, NDSolve seems to be working appropriately. Just as a sidebar, I should probably point out that in solving NDSolve, there are different ways to do it. What I am using is the finite element approach. And so what I have assumed a certain mesh size, and I've kind of maxed out the mesh size for my laptop. So if this thing bombs on me, I may not be able to reproduce my curves because it takes a while to rebuild. So let's look at the solutions. And I should preface before looking at the solutions is that the goal here is, one, take a model, find the exact solutions, and then ask the question, based on the exact solutions, how well do those solutions compare with the qualitative nature that I might get from a streamline approach? So what I will have to do when I come to the streamlines is reemphasize that streamlines in general, I can't compute the normal way, but streamlines in fact are simply the integral curves of a vector field in the geometry. So once I have the vector fields computed, I can always compute the integral curves. So that's what we're going to do. So the first thing I have to do is show you that yes, we can in fact, well, of course we can solve the equations, but we can look at the solutions that we get from the equations. And for example, here are the flow equations for along x and along y and along z, plotted against x and y. And you can see that they have a structure which reflects two things. One, in part, the boundary conditions. So I had some boundary condition here, and that gets reflected inside. Even if I get rid of that boundary condition, however, I will get a structure inside given the nature of the stresses or the gravitational fields that I might impose. So here are the gradients for the player one, the x and the y gradient, or compression if you like. Here's the z compression. And note that inside our boundary, we generate a fairly strong compression inside. So on our scale, if I took everything away, I would hope that this thing is 0, and you know I have a fairly strong compression here. I could compute some other things that might be of interest. In the three-dimensional world, I can compute, say, a velocity, for example, as a density plot. This would be, say, the average velocity in 0.30. So it's 0 in the middle, and it has two sort of lobes on the edge where it shows. Not particularly interested in that right now. So I'm interested in the streamlines, but I do, you know, just to show that yes, you can go through and compute lots of things about the way the fluid looks in this three-dimensional model. Lots of kind of cool things that you can do. So here's what I'm looking for. Okay, I want to compute the streamlines, and as I pointed out, the streamlines are in an exact theory. What I want to look at are the integral curves. I want to look at a curve that moves along the velocity flow, the velocity vector. So given a solution, I need to create yet another differential equation, which gives me the fluid flow, and then compute those. So this is the fluid flow, the behavior of the velocity along x or along y or along z for the different colors, blue, red, green, and they oscillate. So I can see blue goes up and then it goes down, goes up, goes, it just is an oscillatory function, has some ragged structure, which I suspect is more to do with the mesh size than reality. but I do think that some of the structure is really, obviously this big pike is probably irrelevant, but some of the structure is the curve, just oscillatory curve. If I were to take a very simple approximation to streamlines, I would have said that the rate of change of the flow would be proportional to the Coriolis force times the flow. So, sort of V dot A equals F dot V. So that's a simple problem to solve, and it has harmonic solutions, and the harmonic solutions would be based upon the eigenvalues of the antisymmetric matrix F. And so we recover that qualitative behavior in the exact solution. We shouldn't be surprised, which means I don't have to throw away all the stuff that I did before. But nevertheless, I am happy that I see that type of behavior, but I also see some additional structure that I would not have seen in my original two-dimensional, one-dimensional streamlines. So here are the positions. The actual streamline is a function of position, and it averages out a lot of the numerical noise, and I do see maybe this slight thing here is a tweak, but I do see a nice oscillatory behavior for red, for green, and I see some structure in blue that repeats itself. So I see some additional structure which results from looking at the exact solution that I wouldn't have seen before. If I look at the 3D plot, I start to see also some evidence. I have some transient behavior. So if you are familiar with doing behavior, steady state behavior in things like circuits, in electrical circuits, in electrical engineering, it's not uncommon that you start someplace and you're not near a stable behavior, a stable cycle. And so you start wandering around and hit the stable cycle, and then now you go around that stable cycle forever. See the same thing if I plot it as a function of, let's say, the sum of the distance in x plus y versus z. This is my player 1 in the game theory. This is my player 2. Here I start off far away from things. I hit my cycle, and now I start going around, and I now hit a kind of a steady state cycle. What does that look like for those of you that are electrical engineering people? It means that you started a circuit, like an AC circuit, and all of a sudden it now has harmonic behavior, and you're now looking at the harmonics of the system. You've changed from a system that was very simple to a system that's a little bit more complicated. You've added more resistors and capacitors, but now all of a sudden you still see the same harmonic behavior with a little structure in the way in which it goes around its stable curve. I can look at some other things, but I want to move on a little bit and say, how would I go and get more insight into the behavior, in this case, the three-dimensional behavior, by looking at a plot that would be, instead of a one-dimensional streamline, which gives me a two-dimensional plot, what if I could look at multiple streamlines, okay, which would give me a two-dimensional streamline slice into what's going on. That two-dimensional slice I could then look at as a three-dimensional plot. So here would be my two streamlines. I have one streamline associated with variables x and y, and another streamline that's associated with z. As in a sidebar, if I'm doing game theory, player 1 might have 10 such choices, x, y, blah, 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 up to x10, and player 2 might have 20 such choices, z1, z2, blah, 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 z20. I would still have a two-dimensional plot that I could do in terms of S1 and S2, and these curves you can do, in fact, we have done, in fact, for game theory to produce our two-dimensional slices getting three-dimensional plots. So we do that now for this case. now solve two equations, more differential equations. These are two-dimensional integral curves, if you like. So there's no, they're exact. We're not assuming anything about the compressibility, and we compute what I call these effort streams. Oops, I went too far. And I get something as a two-dimensional plot for green is along a streamline. That's a constant S1 minus S2. So a constant streamline. Here's my two-dimensional cycle. And I said I can look at that in 3 dimensions. So let's look at that plot in 3 dimensions. So I have R1, which is X plus Y. I have R2, which is Z. This is my sort of quote player 1. This is my quote player 2. It shows me not just the cyclic behavior of the structure, but it starts to show me how the structure can bend and move in on itself. I really start to get a feeling for the particular behavior of this fluid. And just for ducks, if I just compare that to something that was computed for a game theory calculation I think this was like a model that had, this was a 5-dimensional model, and it has a very similar structure to the one we just did here. So what have we learned, okay? In using 2-dimensional streamlines, we get a picture, we get a 3-dimensional visualization. The Navier-Stokes solutions that we just did show us that qualitative nature is very similar. How should I say it? What do we really conclude from this, okay? We certainly conclude that we replicated the kinds of behaviors that we saw before in game theory. You haven't seen it, but I've seen similar behaviors, and I showed you one example. And so qualitatively, the results agree. What would I like to do? So I thought about this for a while, and I said, okay, if I wanted to take the game theory calculations to the next level of computability and provide a way, a set of notebooks that I could give to non-experts, people that are not experts in partial differential equations, not experts in game theory, but I give them a notebook and I want to give them a reliable way to see the structure of a game, then I need a more reliable way to compute the 1-dimensional and 2-dimensional streamlines. I think what I've learned is that the usual technique that I've been doing so far is not bad, but it would be much better, and so this is my request, it would be much better if I could get a good numerical solution in n dimensions, just like I did here in 3, and then I could use those solutions to produce the streamlines, and I would have a much more accurate representation of what's going on in the game. My understanding, and I may be incorrect, is that right now my ability to do nonlinear partial differential equations is somewhat limited to 3 dimensions. So I guess I'm pushing that we could move the geometry and technology to higher dimensions, or possibly is there a way to, in a slightly different way perhaps, directly get the 1D and 2D streamlines that I want to calculate without solving the full problem. So I think this is a place that I would like to stop and see if I have any questions. And before I take questions, let me just thank you for your attention and for attending the talk.
Professor Thomas, there does appear to be a question in the Pathable chat.
Okay. Could you read it for me and I will answer it?
Certainly. It says, do you use these results in both decision theory and fluid dynamics classes?
Good question. What I have done, I taught a course to software engineers and computer engineers that had no background in Mathematica and no background in game theory or geometry, or for that matter, much of differential equations, calculus in general. It was a 10-week course, and I started using Wolfram's little book on Mathematica. And based on that book, they learned enough Mathematica. I gave them notebooks that allowed them over the course of the 10 weeks to take the 1D and 2-dimensional, 1D and 2D streamlines and compute the results. The result that I showed at the very end is the kind of results that they could do themselves. And they were able to do it, and they were able to analyze it. And in fact, by the end of the quarter, they were able to come up with their own projects in game theory and start talking about what those results meant based upon the analysis of the curves that they got out of it. So I hope that addresses. If you want to talk to me offline, I would be more than happy to talk at great length about that.
There are some additional comments in the Pathable chat. Oh, we just got one more question that says, what does zero compression mean in decision theory? I'm not exactly sure, which is why in decision theory, it's not an assumption that I would normally want to make. Compression in a fluid general has to do with the, if you like, the forces that interact. Okay, if I have something that is zero compression, it means things don't like to come together and they form like a rigid body. I don't know enough yet or have any intuition or insight yet as to how that would truly apply to decisions. So right now, for me, the compression is something that I don't look at as a given assumption. What I do know, however, is the flows have a very specific meaning, because this has to do with the rate at which people make decisions along a particular strategy, how often they pick one strategy versus another. That I can set up as part of the boundary conditions. If you like, in the model I was talking about, that's like I can specify the Vx, the Vy, and Vz. That makes perfect sense. Another thing that makes perfect sense in decisions would be the stresses, the phi1, the phi2 that I put up there. These are stresses that you can relate to actual decision processes. People that are under high stress, like in a business, high stress would actually correspond to a high value associated with making certain kinds of choices. This is something that I could parameterize clearly, and so I can specify those things. I can also specify with some sense that there might be some general attraction that's like the gravitational field. These are generalized in n dimensions in kind of interesting ways. The gravity, which we think of in 3 space, in a general space, comes about because you make an assumption about an isometry, which means a symmetry of the metric that you use to describe the situation. The metric in a game theory is related to the values that people assign to certain decisions. And it's easy to imagine that certain strategies, choices leave the utility unchanged. For example, I may have some internal
choices that I make about how my head works, and these internal choices aren't visible to the outside world. These would be isometries. In this theory of decisions, those isometries, every time I have an isometry, there is a consequence. One is I will always generate a field, a antisymmetric field, which is a payoff. So associated with my internal isometry will be a payoff, and that payoff I associate with the game theory payoff matrix, so that's observable. And if I have isometries in time, that's associated with a, if you like, a payoff that's related to time. We normally see that payoff as a associated with something like a Coriolis force, okay, and a gravitational field. So it's a different way of looking at gravity associated with the asymmetries, the isometries of the situation. So from that perspective, I wouldn't start with an assumption about the compression, but I would point out that by making no assumption about the compression, I generate compression based upon things which I think I do know about, which is my boundary conditions on flows, my understanding of isometries, my understanding of the stresses that might occur. And so maybe my position is I don't want to start off with an assumption about compression because I don't have a sense about that, but I can back into it based upon my understanding of the other stresses of the problem and the boundary conditions I do know about. And again, hopefully that answers your question.
Okay, I'm not seeing any other questions, so it just remains to thank everyone for coming, and thank you, Professor Thomas, for a very interesting talk.
Well, thank you, and thank everybody. Let me thank everybody for your kind attention, and hopefully I'll see some of you during the conference and we can continue the conversation. Thank you.